Ji, Suhail, are you there?
जी मैं इधर ही हूँ ताहिर साहब आई एम हियर
Acha ji, we have 15 participants already joined, and actually those who registered were 20. So let's wait for another 2-3 minutes and then we will start, inshallah ji. So here your video is not coming. Is your video have you switched?
I had put it off.
Okay.
I am having some issue with the light on my face, but it's okay. No issue. No big issue.
ज्यादा हो जाएगा मैंने तो सिर्फ पिछली बार पीती हुई जिसकी डिप करने
Suhail, we are ready to start now. Are you ready?
Yes, I'm ready. Tahir Sahab, I'm ready here.
Thank you, ji. Bismillah ar-Rahman ar-Rahim. A very warm welcome to all the participants who have joined us in the lecture number 35 of Pakistan Society of Civil Engineers. As you know, today's speaker is Engineer Suhail Gibria, and the topic is Liquefaction, Potential of Soils, Study and Mitigation. Before I introduce the speaker, well, he doesn't need an introduction. I think this is his fourth lecture from our platform, and he's a well-known engineer in Pakistan. Anyhow, first I will explain you the rules and then I will introduce the speaker. The rules are the same normal, that all those who are registered for the CPD, they have to keep their webcam on. They should appear live on the screen. Only exception has been given to the ladies. If they want, they can cover their face, but they have to appear live on the screen. Second, during the lecture, all the participants should keep their microphone in mute position so that no background noise disturbs the flow of the speaker. The third is question answer session, which is a 20-minute question answer session at the end of the lecture. But the speaker, I know very well, he allows the questions to be asked during his lecture while he is delivering. So, but during the lecture, please ask your questions through the text message. You just text the message, and when appropriate, convenient, I will read the question to the speaker, and then he will answer it. In any case, the 20 minutes question answer session at the end of the lecture will take place, and there you can ask your question through the microphone. So these were the rules, basic rules which we follow in every lecture. And please keep your webcams, again, I'm reminding, open. You have to appear live on the screen. This is a rule which is set by Pakistan Engineering Council, and it is mandatory. And your microphones should be in mute position. Now, a very brief introduction of the speaker. Engineer Suhail Gibria is an eminent geotechnical engineer of Pakistan. He was born on November 20th, 1957. He has now 41 years of teaching, research, and practicing experience in Pakistan and abroad. Mr. Gibria obtained his bachelor's in civil engineering in 1980 and master's degree in geotechnical engineering in 2004, both from University of Engineering and Technology in Lahore, Pakistan. In between, he studied at Lahore University of Management Sciences, LUMS, and Pakistan Institute of Management, which is PIM, to earn a handful of diplomas. He has acquired a series of trainings and attended a host of seminars, workshops, conferences in Pakistan, Malaysia, South Korea, Nepal, United Kingdom, France, UAE, Oman, as a part of continuing professional development. He has gained significantly rich geotechnical experience of working on diverse engineering projects, including nuclear power plants, irrigation and hydraulic works, dams, sewerage and drainage works. Apart from that, he has earned experience of motorways, buildings, airports, bridges, you name any discipline, he has the experience, to cut it short. He has carried out professional works in Pakistan, Saudi Arabia, Dominica, Afghanistan, Oman, UAE, Qatar, UAE, France, China, and Ethiopia. Mr. Gibria joined UAET initially as a lecturer in the civil engineering department, to most probably in the soil mechanics laboratory, and he must be teaching also soil mechanics there. And after that, he joined NASPAC as a junior engineer, and then he rose to the position of vice president step by step in this organization. He retired from this organization about 5 years back, and today he is still in that organization in its foundation, NASPAC Foundation, and he is head of research and development in the largest in NASPAC Foundation, and he controls the quality of geotechnical engineering department of NASPAC. He is responsible for execution of a variety of projects as a team leader, project manager, by planning the scope, coordinating with clients and other specialties, supervising and guiding a team of engineers and geologists. Mr. Gibria has been lecturing extensively at various fora like UET, Lahore, Government Engineering Academy, Wabda Technical Training Institute, GTZ, Technical Training Program, Pakistan, and then Pakistan Engineering Congress, Institute of Engineers, University of Punjab, Military College of Engineering, Risalpur, NUST, FAST. So there are many other organizations also where he is lecturing extensively. He is an author of over 70 research papers, which have been printed and presented in conferences, seminars in Pakistan and abroad. He is visiting faculty of FAST University, Lahore, adjunct faculty of MCE, Risalpur, and he is the member board of studies of universities of Central Punjab. Mr. Gibria is a member of Pakistan Engineering Council, fellow of Institution of Engineers Pakistan, member of Pakistan Geotechnical Engineering Society, member of American Society of Civil Engineers, member of Pakistan Engineering Congress, member of International Society for Soil Mechanics and Geotechnical Engineering, and founder member. And he's also the founder member of Pakistan Society of Civil Engineers. Mr. Gibria has main interest in soil dynamics, ground improvement, foundation engineering, landslides, problematic soils, field and laboratory practices. Besides high geotechnical capability, he has demonstrated outstanding project management skills too. So this was a very short and a brief introduction of the speaker. And now with this, I hand over the floor to Suhail Gibria to start his lecture. Thank you.
Taisa, thank you very much. Unfortunately, on this laptop, I'm having some trouble with the camera, but I think I am audible, and I think screen share is also visible at the moment.
Yes, screen sharing is visible. You can go ahead.
Okay. Okay. Bismillahirrahmanirrahim, and thank you very much for a bit more detailed introduction. I think audience are in the reasonable number now. How many people are there roughly?
We have 22.
Okay, so let us start. I would say that during the course of lecture, I expect that some more people would be joining up. This is a slightly difficult and slightly dry topic, but in order to inculcate interest and to generate, lively attitude in the lecture, you see, I've done every effort to include pictures and, to give details. So don't get bored up, but this is how geotechnical engineering and some of the topics of geotechnical engineering are. Liquefaction of soils, that is what I'm going to talk about. I'll throw light on its study, analysis, and mitigation. I'll start from giving you brief about the background, about the fundamentals of soil liquefaction, but it is basically, many of you would be knowing it. I'll be letting you know in my own terminology in different ways. Then I'll show you a few glimpses of some known liquefaction-induced hazards which have taken place. What makes the sites to be susceptible or vulnerable to liquefaction, I'll explain to you. And there is cyclic loading and there is static loading called monotonic loading. What is the difference in the behavior of the two so far as the inculcation of liquefaction is concerned? Then I'll explain to some reasonable depth the state-of-the-art methods which are present to carry out the liquefaction analysis, the liquefaction potential determination. So I will be mainly concentrating on the cyclic stress method, and I'll be telling you the difference between free field and non-free field condition. And there is another equivalent method, you see, which is based on strains. You see, either we can base on stresses or we can base on strain. Then in the end, the remediation and mitigation, how to go about controlling it, how to manage it. and if time will be there, some post-liquefaction deformation. And I'll also like to give you some local, not in detail case histories, but I'll be mentioning that in which project what was done. So just start up. You see on the left side here, you see a stable structure, and on the right side, you see liquefaction having taken place. And if you look at the bottom circles, you see sand, grains and water in both. But in the bottom left circle, what you see is that grains of sand are packed densely together. So this is called a solid state behavior. You can see clearly particle contact, you see particle contacts there, so that any load which is imposed from the top can be transferred by grain to grain load transference mechanism. While on the right side you see, after shaking by dynamic forces like earthquake or some other dynamic effect, there is a physical separation between the particles. I think you can clearly see on the right side, lower circle, right side, there's a physical separation. And this is a very clear manifestation of the liquefaction process. This is what is happening within the soil. Particle gets physically separated for a little small interval of time. And when it happens so, they are no longer in the position to have a load transference mechanism, a solid state grain to grain load transference mechanism. So what happens is in this phase, why do they get separated? There's a pressure in the water which keeps them away. A pressure has developed. Why does this pressure develop? There is a condition of very fast loading which doesn't allow water to drain out in the vicinity. Hence, it is undrained condition in which the pressure is now developed in the water called pore water pressure. So this is a very simple explanation of liquefaction. So very generally speaking, we would recognize liquefaction when there are very high pore pressures which have developed. And as a result, since the soil has lost the tendency of bearing the load like a solid state system, it behaves like a liquid for a very small interval of time. What one would expect? Large deformations or tilting, because there is no contact, physical contact between the soil particles. So when we see excessive deformations or excessive loss in strength and kind of sand boils in which under pressure, water under pressure, it is releasing, you see, it is getting released out from certain not only crevices by tearing the ground, you see, from escaping from the ground in some manner, resulting to sand boil. These are all the indications or manifestations of liquefaction.
Suhail,
Yeah,
I'm sorry, I have to interfere. A
please.
small announcement. For all the participants, this is the last time I am announcing that those who have not switched on their webcams, please switch on. After this, there will be no announcement. I can't disturb the speaker, the flow of the speaker time to time again. So please switch on your cameras. And in case your cameras are not switched on, this is very clear, you will not get the CPD certificate. So don't complain afterwards that our certificate is not being issued. So kindly note, this is the last time I'm making the announcement. Further, no announcement will be made in this regard. Thank you. So Suhail, continue, please.
Yeah. So you see, in order to develop liquefaction, what we need to know is what we need to have is rather is seismic environment generally, because of the earthquake loading, you see, which could be there, or some machinery loading, or some, you see, some other vibratory loading, even winds, you see, and strong tidal actions, you see, they would result into liquefaction. And when the condition is of undrained loading, even the static loading called monotonic loading can result into liquefaction failure. So the rate of loading has to be very quick or very high so that there is no opportunity for the pore water to escape, so that the loading remains essentially undrained kind of loading. Generally, we talk of sands with little silt content when liquefaction comes to mind, and they have to be I'll be explaining to you how other soils are also, you see, involved sometimes in the process. Loose to medium dense state of compaction is a must. And the water table has to be either very high or there has to be high moisture content. Here you see some classical cases of liquefaction failure. This is an old record, more than a century old, 1906, and you see in Niigata in Japan, 1964. The overturning of the whole of the apartment was there, or some apartments were tilted, as a result of the liquefaction. And here you see sand boils. I talked of sand boil. What is sand boil? You have a liquefied layer of sand. What will be there in the liquefied layer? Water under high pressure. So it will tend to tear the ground, you see, wherever the ground is weak, and to rise up, you see. Here, above the sandy layer which got liquefied is a cohesive or impervious barrier. So it has just pierced through it and come on the surface. Like this, you see, these are the sand boils. Wherever they are a clear indication of liquefaction. And here you see a vehicle going into sand, and you see somebody standing in a very liquid state of sand. You see this all indication of liquefaction. Here you see in Japan, you see it is Japanese city, how in the grassy ground, sand boiling has taken place, sand with water coming out under immense pressure. So, under all these conditions, when the pore pressures are high and the soil starts behaving like a liquid or fluid, we call it as liquefied. When the soil is liquefied, it has lost its shearing strength. I showed to you in the first slide, physical separation between the particles and water introduced between the particles. So it is a medium with no shearing strength. That is the liquefied soil. So when a saturated or partially saturated soil, high moisture content, substantially loses strength and stiffness because of any applied load. It may be cyclic, it may be vibratory, it may be bomb blast, it may be tidal action, it may be wind, repeated application of wind currents, or it may be even static loading of high magnitude in undrained condition. So what we expect is that the soil is no longer going to bear the load because of the excessive reduction in its load carrying capability, the shearing strength. In soil mechanics, the term liquefied, the word liquefied was first used back in 1918 by Alan Hazard, who did a lot of pioneering work in soil mechanics. And for Calaveras Dam, he described the mechanism of flow there as a result of the liquefaction of the embankment dam. So we expect that in low density materials and in sloping ground, this kind of flow liquefaction will take place. Try to understand, you see this phenomenon from the shear strength behavior of soils. And many of you, rather all of you would be familiar because of your studies in bachelor level between the behavior between the shearing strength and the normal stress. The shearing stress and normal stress in the form of the Coulomb envelope called Phallium envelope, you see. And below this figure, you see there's a small, very common equation for civil engineers. The total stress makeup, the effective stress makeup in the ground is equal to the difference of the total stress at any depth minus the pore water pressure carried by the water in the pores at that depth. So what happens in the liquefaction process? The pore water pressure U increases and the total stress sigma remains the same. Of course, it will be the same. So as U increases, so sigma prime, the effective strength, the strength because of the grain to grain contact, load transference, that decreases. So what will happen if U becomes very high, and if the pore water pressure is almost equal to, sigma, the total stress, your sigma prime effective strength will become 0. So this is the status where the ground loses its entire strength. And that is the onset of the liquefaction, where the effective stresses, they reduce to almost 0 and become very low. So all such conditions in which shearing resistance is lost, we expect production of large strains because of the high forward pressure. Whether the loading be cyclic loading or whether the loading be a static or monotonic loading. So here I would refer to the term of initial liquefaction. It is that condition where effective stress is momentarily lost. It becomes close to 0 during the loading. So soils carry loads at the contact between particles. Give me just 1 minute because the headings of my slides, you see, they are covered with the bar. You see the status bar carrying icons of this software. Just a minute. If I'm able to bring it back, yeah, it's going to go down. Yeah. So why liquefaction occurs? So soil carries load at the contact between particles. So we know that when this soil is dry or the sand is dry, it will be just got shaken up and the voids will be reduced. It will not be liquefaction. Liquefaction will be there when water is there and a saturated loose to medium dense soil in undrained condition. Undrained condition in any soil would develop when the rate of loading is very fast, very quickly, rapidly applied load that doesn't let the water from the pores go out. And when there is a repeated application of such load, like in case of earthquake loading, which comes in very quick cycles, numerous in number. Similarly, the blast loading, which is the cyclic loading, and similarly, there could be a tidal wave loading, or there could be gusts of winds coming and going, coming and going. So these are the loading conditions of cyclic loading. So you can see that the soil behaves in such conditions as a liquid. Just a minute. Just give me a, it's not, why it's not moving? Just a minute, let me see. The presentation on my end, I'm not able to move it. What happens? Just stopped, just frozen. Not moving up and down. Let me stop share and share again. I don't know the reason why it has stopped. Can you see the screen? Hello? Tarsab and others?
Yes,
Anybody?
sir, we can see.
Okay. So, we have already talked about this. Another way to explain liquefaction, if loading is applied and large, it is large enough, it's applied quickly and large enough to see, and so that the water doesn't move out of the pores before the next cycle of the loading. So the pressure will remain there till the next cycle of loading comes, and each cycle of loading in a cyclic loading pattern will be building up a little pore pressure every time, so that the total pore pressure will go on increasing, right? So this loss in the structure deprives the soil to transfer the shear stress that it behaves like a liquid. So here you see in this slide, on the left, you see we have a loose saturated soil with excessive number of voids on the left side. In the intermediate figure, there are contact stresses, anyhow, they are high enough. to transfer the load even in the loose condition. But when there's an earthquake wave which comes as shown on the top, it will cause some physical separation. You can see some of the contacts are lost and the contact stresses between the soil grains have reduced compared to the left-hand side. So this is, you see, the process in which the deformations would increase and the ground will be moving towards gradual failure if the wave pattern continues. In addition to the definition of liquefaction for soils, now the literature says that all cohesive soils having plasticity index less than 15 will also be considered liquefiable, which lose excessive strength and undergo high deformation under seismic shaking. Which kinds of soil those could be? Those could be the sensitive soil. There's another way, you see another model, pictorial model, to demonstrate liquefaction behavior. I have a video, small video. Why not to attempt to run it? Give me 1 minute. I just stop share here and I try to run that video. Just a minute. Let us see. I think it will operate. Just a minute. Let me have the video operated. If I can show that to you, that will generate a lot of interest. Just a minute. Well, not able to access it rightly. So I just go back to the original lecture. Not getting access to it. So on the top left, you see soil grains idealized by circular steel balls. They are having some reasonable grain-to-grain contact. In picture B on the top right, you see because of shaking, there is a physical separation between the soil particles, which is also shown by the idealized steel balls. So this is the generation of the pore pressures. Remember that after this process has taken place, the particles will come back to a denser state of compaction after liquefaction. It is always there. So in the figure C, you see grains packed together more densely than they were even in the initial state A. And look at the steel ball. The voids between them have reduced further. So post-liquefaction, there is settlement, and a soil which has liquefied once will have a little tendency or will develop less strains, less deformation next time for the second liquefaction. Just to have a note the difference, to have a look at the difference between the earthquake loading on the top, a series of, you see, vibrations, and they are receding gradually. Say after 50 seconds, you see the earthquake effect is gone. So this kind of load time diagram or acceleration time diagram is called earthquake history. Earthquake time history in terms of load or acceleration, or it could be even deformation. We cannot produce this kind of condition in the laboratory when we have to carry out simulating tests like cyclic triaxial liquefaction test or like simple shear test in the laboratory. Loading cycles are there, but they are replicated at some number of equivalent uniform stress cycles. They are called equivalent, certain number of equivalent uniform stress cycles. You can see loading and unloading is equal. So every earthquake time history can be converted into some equivalent number of uniform stress cycles based on the magnitude of the earthquake. So a lot of work has been done by Dr. Seed and others that how to transform an earthquake history into equivalent number of uniform stress cycles. And at the bottom, you see our general static loading called monotonic loading, right? So you know a basic difference. If you talk of blast, in blast, the first loading is very high, and as you move away, the effect of the shock wave reduces. But a blast shock wave essentially goes like this. Look at the figure on the left in red. The highest loading cycle is the first one, that every subsequent loading cycle will be lower value. And you can see also in the recorded blast history on the right side in blue color. So it could be monotonic loading or cyclic loading. Now, I want to take the concept and you too, that in addition to sands, which could be loose to medium dense, when the loading is very high, like blast loading could be very high or a very high earthquake, you see, very high energy release, a high magnitude earthquake whose focal depth is low, like 10 kilometers, like 15 kilometers, like less than 10 kilometers. So even sand gravels in loose medium dense condition or even non-plastic cells may get liquefied. And there are recorded case histories of such liquefaction having taken place. So first time the concept of evaluation of and study of liquefaction that took place on the basis of the 1964 Good Friday Alaska earthquake and Niigata, Japan earthquake. This is where the development of liquefaction in numerical terms started. I would not be able to show you this video right now. So here, there are three kinds of liquefaction phenomenon now. Let's go into the detail. There are three distinct types of liquefaction phenomenon recognized. It is not just one type. One is called flow liquefaction, in which the liquefiable material flows at certain slope. This is the characteristic of the sloping ground. But even in flat ground, liquefaction would take place. So cyclic mobility and cyclic liquefaction are generally talked about in a flat ground condition, even when slope is not there, or it is very mildly sloping. So let us draw the contrast and the difference between the two. The first term, the flow liquefaction, is specifically reserved for the situation when the shear stress is more, the applied shear stress is more, and the resisting shear strength is less. You know, it is basically flow liquefaction is basically the imbalance between the applied shearing stress and the resisting shearing strength. If on any plane where sliding can take place, if applied shearing stress is more, flow will take place in a sloping ground. So embankment dams have failed in this manner, or the sloping grounds have failed this manner, in which there has been an imbalance. The shearing stresses have been higher. It could be monotonic or even cyclic. So the result is a sudden catastrophe. And this kind of phenomenon is also understood for sensitive clays. What are sensitive clays? Clays which have a card house like honeycomb type structure having excessive void, especially deposited in marine environment, so that their undisturbed strength is very high compared to their disturbed or remolded or shaken strength. If the ratio of the undisturbed to the disturbed strength or shaken strength is like 4 or more than this, we will call them sensitive clays essentially. But if it is very high, the ratio of the undisturbed to the remolded strength is very high, we'll call them quick clays. In contrast, there is a term called quicksand also. So that is precisely not the name of a sand, rather it is the name of a phenomenon in which water is introduced into sandy ground from some external source, resulting into high water pressure, so that the confining pressure downward is less and the upward pressure due to water is high, and the sand gets boiled up. That is called a quicksand. Quicksand and the sand boiling is the same thing. Here I'm telling you the quick clay. The pressure of a new building on sensitive soil should not be that much. You see, the weight of the ground and the weight of the structure should not be that much that it can break the structure of the sensitive soil. Otherwise, you see, this thing will happen. And if earthquake shaking can do it, it will break down the sensitive ground, again resulting into large deformation. So I was talking of the flow liquefaction in which you see earthquake force, earthquake has come, red horizontal line indicates shearing strength. Result is the failure, you see, because of imbalance. So this is defined generally for slope less than 5%. All the slopes, sorry, more than 5%. And the ground is said to be in a condition called strain softening. The examples have been Suhail dams and Lower San Fernando Dam. What is strain softening? When we talk of strain softening or strain hardening or elastic plastic behavior, let's have a glimpse. It's, you see, revamping of your basic knowledge of mechanics of civil engineering. But it's good, you know. I told you that it will the lecture could be felt slightly dry by some of you. But if I am delivering a lecture on liquefaction evaluation, it has to be dry, you see. You have to understand it is a serious talk. So here you see the strain softening phenomenon, the relationship between stress and strain, where after a certain value of stress, there is enormous increase in strain and stress goes on reducing. Soil is no longer able to take high, not able to show high resistance. It has softened. But if after a certain value, soil starts, the medium starts getting again high value of stress and the strain is developing. So it is called strain hardening. Very simple concept. If it remains constant, if the stress doesn't increase or decrease and strain goes on developing, it is elastic plastic behavior of the medium. So we have these all three behaviors manifested in soil in different conditions. So I think, given you a little dose of this uh, flow liquefaction. Second term is the cyclic mobility. What is it? Cyclic mobility, as the name suggests, it is not under monotonic. It is only under the cyclic loading because of the any condition. As I've been telling you, there could be many conditions of cyclic loading. Any condition of cyclic loading would cause this condition. But in this condition, very interesting, the static shear stress, the shear stress is less than the shear stress. Even then, you see, we call this cyclic mobility a kind of liquefaction because the deformations are excessive. Overwater pressures have not reached a very high value like 100%, but the deformation is very high. So it can occur in almost in any saturated sand, provided the cyclic loading magnitude and duration. I mean, it's a number of loading unloading cycles. If the duration is long, then this means that the number of cycles of loading unloading will be enormous. So that condition can induce cyclic mobility, excessive deformation. But being civil engineers, if our structure, our works are there on such ground in which cyclic mobility can take place, so it is gradual, you see, loss of strength and gradual accumulation of the deformations. So in geotechnical engineering, there's a term called lateral spreading, and it is commonly understood to be a kind of situation because of cyclic mobility and permanent deformations. So it happens in grounds, you see, which are almost flat or very gentle, less than 3% slopes. Soils can reach almost zero effective strength, but generally not in this kind of situation. This means the pore pressure doesn't reduce to zero and the effective strength is not, water pressure doesn't reduce to 100% and the effective strength doesn't go down to zero. Even then this kind of cyclic mobility or liquefaction takes place. Here, just have a look, you see in these figures, just to revamp your knowledge of when I'm talking again and again of pore water pressure. So look at the lower figure in which it is given figure 6. On the left-hand side is a triangular diagram indicating the total stress distribution in a ground having H1, the first layer of H1 thickness with gamma 1, and then water table is there. The below two layers of H1, H2, and H2 thickness are all saturated. So in that saturated zone in the two layers, we have the neutral stresses. It is written natural, it is neutral. Basically, it's a type of mistake, which are the pore water pressure. And the third figure, effective stress, is basically the difference, subtraction of the neutral stress of the pore water pressure from the total stress. So this is how the definition goes. Again, in cyclic mobility, we do expect sand boils, you see. There are oscillations of the ground, and you see there's a kind of situation in which the shearing stress is less, but the shearing strength is more. But even then, repeated application of loads for longer duration of time results into this situation. And of course, when there are ground oscillations, you expect to see deformation movements and damage to the structure. There could be sand boils. Now the third term. So third term is called cyclic liquefaction. Cyclic liquefaction. So it is a temporary condition, as I told you in the beginning, in which the ground loses, because of the cyclic loading, its strength in totality for little interval of time. So initial liquefaction takes place. Thus, effective strength essentially goes down to zero, and the pore water pressures, they rise to almost 100%. So we can expect very large deformation with this phenomenon, and this could be sudden compared to cyclic mobility. Cyclic liquefaction is more sudden. Here in this flow chart, I am just trying to tell you that on the left-hand side, you can see the second row of blocks, strain softening behavior. That is what we call in flow liquefaction, which takes place in sloping ground when the shearing stress is higher than the shearing strength. On the right-hand side, strain hardening behavior, and it can have in the below, blocks, you can see two blocks with red circles, cyclic liquefaction and cyclic mobility. They are the manifestation or the result of the strain hardening. Both are because of that, and of course, large deformations. So I've told you very briefly. I have to look at the time also, so I'm explaining briefly, but I have to put in theoretical details. Without going into theoretical detail, you will not grasp the concept and concepts of different modes of liquefaction. Look at these figures. Again, sand boils, bearing capacity failures are there, flotation of ground, damage to foundation, uplifting of utility pipes of sewage or water supply. And here you see, alongside the railway track, we have sand boils, liquefaction having taken place on the structures, which are the retaining structures. Some are on the seashore too. You can see the cracks and movements and deformation. Very critical liquefaction having taken place. And some of you might be remembering the history of Kobe 1919 earthquake in Japan, and this Chichi Taiwan earthquake 1999, where big structures, even flyovers, they look like card made, you see. The buildings collapsed as if they were made of card and very weak and very fragile. Total failure. Of course, when there is no support in the ground, when liquefaction is really there, then there is really no support in the ground for little interval of time, maybe a few seconds, maybe 3 seconds, maybe 5 seconds. But this is enough for the civil engineering work to damage completely or to tilt completely. Look at the fate of the bridges and the flyovers. California 1989, Kobe 1995. And here you see in Alaska, spreading, ground spreading, snow-covered landscape, and then there is spreading, you see, because of liquefaction. So perhaps cyclic mobility type liquefaction has taken place, in which there is gradual collapse. Very famous San Fernando Dam, 1971. You can see the whole dam structure going down the lake side, slope stability, serious issues. Niigata, again, I think you saw the image in some previous slide in the beginning. Turkey in 1909 earthquake because of liquefaction. One whole apartment structure tilted. Here you see settlements, you see, on the right side, you see the building has gone down compared to the platform of the floor level. It has sunk, you see. And there is a longitudinal fracture or crack in Alaska in 1964. You see, between the dam, you see. Here, you can see the level difference of the two lanes of the road. One lane has gone down with vehicles. This is because of the liquefaction effect on that side, more prominent. Here you see a lot of structural damage to the structures. Northridge in 1994, serious damage to the core. Mexico City was a very famous quake in the Mexico Valley, which used to be said to be attributed to double resonance phenomenon. I will not discuss the detail here, that itself is a lot of detail. In 1985, San Francisco, collapse of the structure on the right side and as well on the left side back in 1975. Peru, 2007, Chile, 1960. So we are fortunate, we don't see commonly the failures because of liquefaction, but it doesn't mean that we don't have grounds prone to liquefaction. We do have ground conditions and the structures there. And some important works have been such that the liquefaction risk has been mitigated before construction. I'll tell you a few local case histories where we had to mitigate the risk of liquefaction because of the importance of the works. Peru 2007, a prison site collapses. And here you see how the buried utility pipes and even buried tanks, you see, they come up. You see, they float, you see, when liquefaction is there, the ground is like liquid. So tanks and other things will start floating. Susceptibility, what are the factors for susceptibility? One is the saturation, in very clear terms, or close to saturation. Second is the geological history. Older deposits less susceptible to liquefaction. Why? Number one, because they might have already undergone liquefaction, number one. Number two, cementation because of the edging effect could develop between the soil particles, giving more strength or resilience against development of forward pressure upon shaking. So, the old deposit because of the geological history, so that is a safety situation. Then it is a composition, you see, even the particle size, shape, and gradation matter. Like a rounded particle, sands with the rounded particle will have more susceptibility to liquefaction because in angular particle, there is some more interlocking. There is less interlocking and less frictional resistance in rounded particle. So well-graded soils are more compact. There are lesser voids compared to the poorly graded or soil with uniform gradation. So similarly, clays may generally not be susceptible except when they are sensitive clays and they can undergo high deformation and lose the strength excessively. And when there are sands, they have high silt content. So their susceptibility or risk to liquefaction will reduce. So similarly, deeper deposits, with depth, the liquefaction risk, even if the soils are weak, but deeper weak soils are less susceptible because the dynamic shearing stresses there are of lower value than the threshold value. So it is the duration, the number of cycles that matters a lot. The same earthquake, if it is longer, it can induce liquefaction in the same deposit because of its merely longer duration. And in the initial state of liquefaction would be there because of contractive and dilative behavior of soil. Loose soils have contraction, reduction in volume in undrained condition. So that causes reduction in the effective strength. So loss in the grain to grain stress transference mechanism or reduction in that. So in contrast, the denser soils, they tend to dilate when shaken. So they increase in the effective strength because of the generation of negative core pressures under such behavior. Thus, this becomes the reverse. The contractive and the dilative behaviors of sands upon shaking. For cohesive soils, there is a Chinese criteria, although it is outdated, but there is no harm in telling you. And Seed and Idris, the pioneers of liquefaction evaluation at the University of California at Berkeley back in 1985, they also worked on that. So it has been found by them at that time that for soils having finers less than 5 microns of up to 15% and liquid limit like 35%, if the natural water content is very high, close to liquid limit, then they will undergo liquefaction. You see, this is the old Chinese criterion, but later research has confirmed that it may not be that true in many situations. You see, liquefaction evaluation has evolved gradually back from 1971 and up to year 2000, a lot of work had been done in 30 years. Now 20 more years have passed. We can say the history of development of and understanding of liquefaction evaluation is 50 years old, half a century. So the phenomenon is quite rightly understood now, and the means available to identify and to analyze are quite, precise, and the mitigative measures which will really avert the risk of liquefaction are really comprehensively understood, and when they are applied, there is no liquefaction. So it is said by Robertson and Wright back in 1998 that there is an index that defines soil behavior type index. So this is the cumulative interplay of grain size and its shape and their orientation. So this is an index they define. It is defined in some mathematical terms. They say it is more than 2.6. Perhaps the soil will have clay-like behavior, more clay-like behavior. So it will not manifest liquefaction. I'll show you in some later slide how to calculate this soil behavior type index I sub C. So Robin Fell also found out that when IC is between 2.6 and between 2.6 and 2.9, the soils may be potentially liquefiable. You see, so there has been advancement and improvement in the understanding, the knowledge of liquefaction. It was in 2003 that Seed and his co-workers, they discovered that even coarser gravelly soil, silty, silts and silty clays may also be subjected to liquefaction. So what is that which brings liquefaction in these materials which are otherwise resistant to liquefaction? It is simply the high magnitude of the earthquake, number one, the duration of the earthquake, and the number of loading cycles and the magnitude of the loading cycles in that earthquake, which matter, which can bring out, deformation and liquefaction in these soils. For an example, I can say that ordinarily in dense sands, we don't expect the liquefaction by ordinary means like ordinary earthquakes to take place. But when there is a big bomb blast, even dense sands can liquefy for a very small interval of time. You see, this is a queer and a weird concept now that I'm giving, but this is the reality. There are many papers which have come out The liquefaction because of the bomb blast like impacts, which generate very high pore pressure. So they are able sometimes to liquefy even the dense sand. So here underlies the importance of making our classified our defense works in liquefiable areas very robust and very strong, even against bomb blast. I'll, if time is there, I'll tell you briefly a small case history of such a situation. Back in 1982, Seed and Italy's, they gave a method which was considered somewhat non-conservative with soil with high clay size fraction. So this found out that plasticity was more important than the clay size fraction. That was a kind of research. They used A-line chart and divided the A-line chart into three zones, A, B, and C. You can see in the bottom left corner, soils A, zone A. All the soil which plot here based on liquidity and plasticity index. I mean, they are reasonably cohesive soil generally, though potentially liquefiable. And the soils in zone B, you see, they may be liquefiable, lesser degree. I either assume liquefiable or perform the test. The soil in zone C are generally the outer zone, the zone of this A-line chart, beyond zone B is all zone C. So the soil, if plotting it, zone C, of course, cohesive soil again, generally, will not be considered to get liquefied. So I'm giving you weird concepts about liquefaction today. It's not only the story of loose to medium dense sand. As I'm taking the concept to an advanced level, I have said even dense sand in certain conditions will get liquefied. I have also said that even gravels and silts will get liquefied. I've also said that cohesive soil and clays will also get liquefied, but in certain conditions, not always. So the classic general definition of liquefaction is still uh, towards sands you see in loose to medium dense condition and with high ground water table and shaken with high dynamic forces. I'm speaking myself a lot. I wonder if there is some question from some participant. If you're listening with interest, do you have some question, some query? If there is some query, some question, please do ask me. I stop here for a while. Anybody? Nobody. So I go ahead. So I'll tell you another criterion is Hunter and Fell. They gathered data from case studies where liquefaction occurred and data which did not indicate liquefaction. So they, developed a kind of boundary line or kind of discrimination line between where liquefaction takes place because of the certain effects, and particle size effect also is one of the effects, but that is not the known effect. But they have given some, you say in the shaded area, they have given certain conditions that in these areas, 1, 2, 3, 4, 5, in these projects, in these years, anyhow, liquefaction did take place for these grain sizes. So you can see there are generally, there's a big range of grain sizes of soils which have been liquefied in different parts of the world, but in different conditions of liquefaction under static and earthquake loading. So this becomes a very broad topic. So here, in 2006 and 2008, Boulanger and Idris, they said that soils which exhibit sand-like behavior and liquefied soils which exhibit clay-like behavior under cyclic loading, they have to be discriminated. How? Based on cyclic laboratory tests, cyclic triaxial liquefaction test. So they said the soil more than having PI, plasticity index more than 7, can reasonably be expected to exhibit clay-like behavior. So more resistant to liquefaction. But soil with less than 7 pi probably are more prone to liquefaction. But this is the general criteria. I just wanted to go through this and to let you know that Boulanger and Idris have also done this kind of work based on the plasticity index. So this is different from the earlier work which I gave you. So here the black dots, black circles indicate the clay-like behavior, not expected to liquefy, and very few, you see empty circles. They show sand-like behavior, plotting at the bottom. And there is an intermediate behavior also, which could or which could not. But one has to carry out cyclic triaxial liquefaction test for that. So having said this, I will now give you a little explanation of soil behavior during the undrained loading under static and cyclic conditions. I will take you to the concept of critical void ratio, but I will try to explain in very simple terms. In the upper left diagram, it's a simple stress versus strain curve. If we have a loose sand, it will attain the highest value of stress, and then the stress will remain constant during the laboratory test, right? But if we test a dense sand out of the same soil, a dense medium, it will show a peak value which will drop after further straining, but assume the same value, static value, same stable value of the stress afterwards. So this is called the residual strength of soils. This residual strength of soil tends to show the soil at the same density, at the same void ratio, which is a constant void ratio. It is called critical void ratio. So I just wanted to give you in brief terms, because it is important to tell you that liquefaction understanding in terms of critical void ratio is important. If the soil's natural void ratio in its natural condition is higher than the critical void ratio, clearly it will be susceptible to liquefaction. So that will be a loose soil. If a soil's natural void ratio is less than the critical void ratio, it is already in a compacted state. So it will be a dense soil, not susceptible to liquefaction. That is how we geotechnical engineers from the void ratios A1, study of void ratios, we draw very big conclusions about the susceptibility or non-susceptibility of liquefaction. Similarly, during the static laboratory testing, like static triaxial compression tests in undrained condition, if a soil shows positive pore water pressures at failure, that is indicating high pore water pressures, failure because of liquefaction in the monotonic loading. If under static triaxial test, soil shows negative pore water pressure, that will be a dense condition, not susceptible to liquefaction failure. So there are very clear indicators. But in the liquefaction business, we have some quantifiable measures and some qualitative measures. These are the qualitative assessments, you see, which lead to the qualitative assessment that liquefaction will take place or will not take place. But how much adverse the effect could be is based on the quantitative analysis, which now I'll be coming. Look here. This is a common in soil engineering, a common graph between void ratio on the vertical axis and the log of the pressure, the confining pressure, sigma prime 3c on the horizontal axis. On log scale, this got to be a horizontal line. This got to be a straight line. And this is called the steady state line sometimes. Constant void ratio line, steady state line, right? Any soil whose void ratio and confining pressure plot above this line, they will indicate liquefiable soil straight away. If it plots below the line, it will indicate a dense soil, not liquefiable. A very common test for us, you see, to just have a very correct wheel. And here, this kind of plot is called stress path plot. You see, the Q is called QP in soil engineering. So here we also get a feel that the dilative soils plot above you see, they are not liquefiable. And right away from this plot, we get the feeling that the contractive soils which plot below the dilative, they are liquefiable. Here I take you to a concept of cyclic mobility, how we establish it during the cyclic triaxial liquefaction test. But you will have to bear with me. You see, don't think that it is very difficult, getting difficult and boring and try. But if I don't tell you, I will not do justice with the concept of liquefaction understanding given to you. So here on the left side, look at three figures. You see the top left figure shows a series of loading unloading cycles as we experience in a cyclic triaxial liquefaction test. You can see that the test ends, the loading unloading ends at points close to A and B, you see. They mark close to the end. In the figure right below it, there's pore water pressure. The first one was the loading diagram, the loading unloading cycle to which the soil specimen is subjected in the laboratory. Then pore water pressure, you see, pore water pressure one, when the RU value, pore water pressure ratio is 1 at that stage. When pore water pressure ratio is 1, we mean, look at the small formula written on the top right hand side, delta U of sigma 3C. The change in pore pressure divided by the confining pressure. When the pore pressure change becomes equal to the confining pressure, we say 100% pore water pressure generation has taken place. So this is what has happened on the left-hand side in the intermediate figure where RU is 1. It is 100% pore water pressure. And this is where further loading unloading stops. And look at the third figure behind them. That is the strain development. The strains were low in the beginning and they become very high at the onset of 100% pore water pressure generation. Look, so I just wanted to give you this feeling. Evaluating liquefaction potential. Lot of discussion having taken place on the qualitative measurement, qualitative assessment. Now let's go to the quantitative part. There's a procedure called Simplified procedure to evaluate liquefaction potential given by Seed and Idris back in 1971, published for the first time in the American Society of Civil Engineers Journal of Geotechnical Engineering, based on their pioneering work at University of California at Berkeley at Earthquake Engineering Research Institute, ERI. First time this paper came to give us that how we can calculate the liquefaction potential in quantitative terms, in numerical terms. So they have been collecting, so there has been a largely empirical development over this over 30 years until 2000. Then researches continued and there have been works published in 1996 and 1998 to refine certain coefficients and parameters in the original work. And then finally in 2001, there was a very good paper published by Yud et al. On liquefaction resistance of soil. So his modifications continue even to date. There has been a cyclic stress approach to calculate quantitatively the liquefaction assessment, and there is a cyclic strain approach given by Dorby. The cyclic stress approach is due to seed and release in the beginning, and Dorby gave the cyclic strain approach because whenever there is some development of stresses as a general civil engineer, whenever there is application of stress, some strain will be accompanied. So what if in place of stresses, we compare the developed strain with the threshold value of strain and find out the conclusion about the liquefiable or non-liquefiable behavior of the soil. Then there are some other methods also. Let's not concentrate on those. So I go straight away in the seed and Idris method, first of all. You know, what they have done is, like any civil engineering terminology, we use the term factor of safety, which is generally the resistance divided by the load. You see, in very, very common terms. In soil terminology, when we talk of slope engineering, sliding, we say the D is the stabilizing force is divided by the stabilizing force. So what they did basically in the liquefaction business is that they tried to collect all the data where the ground under certain earthquake conditions got liquefied, and in other ground conditions it didn't get liquefied for some given magnitude of earthquake, for some almost same value of earthquake. So this kind of data was plotted between the resistance or the capacity of the ground or the resilience of the ground to resist liquefaction, and load means the stress is imposed because of the shaking by earthquake. You know, any load during seismic shaking will be the earthquake loading, and any resistance during the seismic shaking will be the resistance or resilience shown by the ground itself, that how strong the ground is, not to allow the development of high pore water pressure. So they drew a boundary line between the sites which got liquefied and which didn't get liquefied. So this becomes the basis of, you see, their initial research work and study. And then they introduced a term called CSR, called Cyclic Stress Ratio. It is the ratio of the shear stress at any depth in the ground divided by the effective vertical overburden stress at the same depth. किसी भी depth पे we have an effective vertical overburden stress. As the depth increases, the shearing resistance of the ground will increase, and the value of the induced shearing stress by earthquake will reduce. This is what happens, you see, in the cyclic stress ratio. So they have given this kind of relationship based on the equation, Newtonian equation, F is equal to ma. Basic philosophy is the same. We can calculate, this is the cyclic stress ratio induced by earthquake. So it is based on the shear stress induced by earthquake. It should be taken like a force, like you are testing a beam or a cylinder in civil engineering. So you see that we compare the imposed stress or imposed load with the resistance with the strength. So similarly, these equations give you a way to calculate the imposed stress in terms of cyclic stress ratio because of earthquake. So this be taken as a load or as a force. Computer programs are also available like Deep Soil or Flash or Shake to calculate this cyclic stress ratio in place of this simple equation in more accurate terms. So one term is this. Now I take you over to the Pakistan's zoning map. It's old one though. Published one is the old one by Ministry of Housing. It divides Pakistan into 5 zones, having different peak ground acceleration ranges. So these peak ground acceleration ranges are prone to generate certain earthquakes, certain peak ground acceleration called PGA or Amax in this above equation. Amax is the PGA value, the peak ground acceleration value, which is can be derived from this kind of zoning map of Pakistan, or some site-specific studies can be carried out. Anyway, they also proposed that this value uh, is slightly high, and this must be reduced uh, by a certain factor called stress reduction factor. And this study was initially confined to 15 to 20 meters depth, and this amounts to the flexibility of the soil profile. That because of the some flexibility in the soil profile, the stresses which are induced by earthquake may be reduced by a certain value, and this graph gives you the value, the way to find out from the average curve at any depth the stress reduction factor, right? RD. So now I give you the concept of equivalent uniform stress cycle, which is quite important. Laboratory data from which liquefaction resistance can be estimated are usually obtained from tests in which we carry out cyclic triaxial liquefaction tests. So comparison of earthquake-induced loading with laboratory resistance requires conversion of an irregular time history of shear stress to an equivalent number of uniform stress cycles. So it is simply an attempt to convert an irregular and excessive number, maybe like 300, 500 stress cycles of earthquake and different in magnitude into some clearly defined few number of equivalent uniform stress cycles. Like this earthquake is having, many irregular loading and unloading cycles. On the left-hand side, you see the shear stress time history. But on the right side, you see a plot between the earthquake magnitude and the equivalent number of significant stress cycles of uniform magnitude. For instance, if we have a 7 magnitude earthquake, you can see if you read on the mean line, we'll have equivalent stress cycles only 10 in number. You see, for so many actually different loading unloading cycles of different magnitudes, we have equivalent uniform stress cycles only 10. So you can similarly estimate this value for any other number. Back in 2005 in Kashmir, our famous Kashmir earthquake, it was of magnitude 7.6. So you can roughly read on the mean line, perhaps close to 15 or 16 will be the equivalent number of significant stress cycles at 65% of the average stress, at 65% of the average acceleration value of the peak value, right? So here I show you an acceleration time history of 7 magnitude earthquake. So here 1260 value is shown to be the peak value, right, for this of the horizontal shear stress. Here we go back to the SEED's 1975 study to estimate for magnitude 7 about 10 equivalent number of stress cycles for the average 65% multiplied by the maximum shear stress, we use the average shear stress, or average is called also average peak ground acceleration. So here you see the same earthquake converted into 10 cycles of equivalent uniform stress cycles, right? And here you see the magnitude of each stress cycle is 819 pounds per square foot cyclic shear stress compared to this one in which one peak value is 126 PSM and others all are less, but their number is enormous, up to 25-second duration. So this is important to find out that how do we determine? So its methods are available. Now I also, before going ahead, will like to give you the concept of free field and non-free field liquefaction resistance evaluation. Any liquefaction potential evaluation where we don't consider the structure like a building, like a power plant, like a bridge, or like a dam, it is called a free field condition, considering that the structure, the works are not there. And if it is possible to analyze the liquefaction potential of the ground with the structure sitting on the ground, because that will impose high pressures. So we can account for the high pressures and consider that in our evaluation to find out the liquefaction potential called non-free field liquefaction potential evaluation. So whereas Seed and Idris did a lot of work for free field condition, Seed and Rollins did a lot of pioneering work to find out liquefaction potential for non-free field conditions. But I tell you that even in the most advanced analysis in any project, even to date, it is a free field evaluation which are considered to be the state of the art. It is not the non-free field condition. There are several reasons for that. There are certain ambiguities which are still in the process of research. Here I want to tell you the difference, that what is the significance of number of loading cycles on bringing the liquefaction earlier or later. If we have a medium dense sand like relative density 47% in the left figure, only 7-8 cycles are just sufficient to bring liquefaction and the pore water pressure to be very high. But if we have densely compacted sand like relative density DR 75%, it will require significantly higher number of the same equivalent uniform stress cycle. This is what you see that denseness of the sand deposit, same sand densely compacted, will require higher number of significant uniform stress cycle to cause high pore water pressure generation, as you see in the figures. I think it is the last diagram, the last part of both the figures shows you pore water pressure, that when it becomes almost one, it becomes one quickly in low relative density, or loose sand, and takes more time and more stress cycle, more duration. So longer earthquake would be needed with higher stresses for the dense sand to get liquefied. So conclusion is loose soils, loose sand can get liquefied quickly in a few seconds, and dense soil will require maybe thousands of cycles and longer time, to get liquefied. If there's a high earthquake but lesser number of cycles, it will not liquefy dense sands. So, pardon?
We have a question.
Yeah, please. I was eagerly waiting for a question. So thank God, one question has come.
No, three questions are there by one person. Mr. Furkan is asking. I will read all the three questions together. First, how can we differentiate to find out that settlement is general or liquefaction prone?
Second one by one. Please ask.
Okay.
One by one.
Go ahead. Answer it.
Okay. We will carry out certain tests at the site and in the laboratory to find out whether the soil is liquefiable or not. We'll find out from the, from the qualitative methods, as I told you, the pore pressures being positive or negative, and from the void ratios being below critical void ratio or above critical void ratio as very positive indicators to qualitatively tell us that the soil could be liquefiable or not. And then we will carry out some in situ and some laboratory tests and go into rigorous analysis to confirm whether this deformation which has taken place is because of liquefaction or because of some other effect. G, next question.
Next one is...
Next question, please.
Yeah, next question is, what are the most commonly used field tests to find out the intensity of liquefaction?
Well, I'm coming in my subsequent slide very near, but I just tell you as an answer to this question. Standard penetration test has a large database and large history for evaluation of liquefaction potential in United States, in Canada, in North America, and in our country too, but less popular in Europe. In Europe, it is a cone penetration test, which has been used abundantly to establish the liquefaction potential, and shear wave velocity measurement has been sparsely used to identify the liquefaction potential, and borehole pressure meter test has also been occasionally used to correlate to this phenomenon. But the major database has been basically in SPT and in CPT. But many agencies recognize that SPT is a bit crude test and CPT is a more refined test. But there is a standard limitation. If we have to assess deep liquefaction, generally our CPT rigs cannot take the test to the very deep level. Such is the mechanism of the test that a lot of load and pressure would be required. So generally in Pakistan, I think Mr. Tahir knows, I think from his own experience, that this 10 ton and 10 types rigs in Punjab sand, they are not able to penetrate beyond, I think, 15, 20, 25 meters. But we have the requirement of evaluation of liquefaction potential to much deeper depths like 50, 60 meters. So it will be inevitable in those cases to rely just on the standard penetration test. And I tell you the basic work of Seed and Idris, he did the pioneering work. CPT came later. The basic work, the basic research is for SPT, not for CPT. A third question?
No, I was mistaken. Only two questions. Go ahead.
Or two, okay. But I'm praying that more questions would come because the lecture will come back.
Suhail, a third one has come. Just
Very good.
somebody popped in. Just.
Very good.
This is Mr. Uzair Akram. He is asking, sir, I am a fresh engineer. I find it very difficult to differentiate between seepage pressure and pore water pressure. Could you please shed some light in this? Now you will have, this is a different subject, I think. So
No,
would you like to answer in few words, or after the lecture you can answer it?
No, I will answer him very briefly. Any pressure, whether in a natural condition or by induced condition, will become pore water pressure, right? Now it is a separate story whether this is the neutral stress or this is the excess hydrostatic, this is the hydrostatic pressure or excess pore water pressure. So seepages which give rise to pressure in the standpipe over and above the natural hydrostatic pressure will be giving rise to higher pressure. So that will be the higher pore water pressure. पोर वाटर प्रेशर तो पोर्स के अंदर जो पानी का प्रेशर है वो है, चाहे वो नेचुरल है चाहे वो बढ़ा हुआ है. स्टैंड पाइप पेजामीटर लगा के रखिए और देख लीजिए कि वो नेचुरल से बढ़ गया है तो वो इंक्रीज पोर वाटर प्रेशर है बिकॉज ऑफ द सीपेज. ओके, आई थिंक इट इज क्लियर.
Yeah, I think you answered it well. So continue with your lecture, please.
Okay, so here you see, well, let's go further. In the laboratory, in the cyclic triaxial liquefaction test, what we do is that we prepare specimens.
Suhail, a minute. I think this is a relevant question. You answer it. This is again from Mr. Furkan. He's saying there is a geophysical test called electric resistivity test. Can we use that to find out the liquefaction potential, as we will get less resistive ground with less groundwater?
There is very little database of resistivity measurements correlated to the liquefaction potential. There are several factors you see. One factor I can tell you is that some, you can say, increase or decrease in the moisture content, some increase or decrease in the salt content will increase or decrease the current transmissivity excessively low or high. So that will make the things dubious. So you see, a liquefiable ground with less salt content may not be indicated that properly, you see. And sometimes when there is high salt content and the ground is not liquefiable, it may be indicated dubiously that it is liquefiable because high transmissibility of current is there. You see, or I am speaking the other way around. You see, when there are more voids in the soil, the current transmissivity reduces. Okay, but at the same time, if in the same ground there are more salts, the current transmission will increase. So you can yourself gauge if there is more moisture, the current transmission will increase. So it doesn't give, a reliable way. So that's why it is no. Similarly, as I told you, even shear wave velocity measurements, they depend on so many factors. So they don't give you very reliable base. They just, I can say, are qualitative measures, you see. But at least resistivity measurement has not been used, you see, to establish this phenomenon, right? Now talking of the cyclic triaxial liquefaction test, here you see the relationship on the vertical axis between the cyclic deviated stress, which is applied during the test to the soil specimen. And we have to see that for a soil of a certain density, how many loading cycles, uniform stress cycles, as I showed you in the previous slide, it will take to get liquefied. So if we prepare a specimen and you see, we prepare specimens at different void ratios. If we use a high stress cycle, high value of stress, the liquefaction will take place at a lower number of cycles. If we reduce the magnitude of the stress in the uniform stress cycle, then it will require for a given void ratio or a given density higher number of cycles. So this is what this correlation shows. Sand specimens compacted to different void ratios, or you can say to different densities, right? Or to different relative densities. And in each group of void ratio or density, we have been using different specimens subjected to different uniform stress cycles, different magnitude of uniform stress cycle. So we get these relationships. And now we see that in our condition, what is the in the earthquake that is in our condition, what is the actual magnitude you see? So it is the comparison of that you see which tells us that that magnitude of earthquake will result into so many number of stress cycles, and that will give us from the laboratory the cyclic deviated stress for the actual field condition. I think you got my point of view. Like in the previous example, I showed you that for magnitude 7, there are 10 stress cycles. Yeah, 10 stress cycles for magnitude 7 in this example. So we will see that 10 cycles here for a given void ratio or a given density will be giving you how much cyclic deviated stress to liquefy, right? So that is your resistance. This deviated stress divided by, you see, this is a shearing strength. In fact, it will be divided by the normal stress to give you the cyclic stress ratio of resistance of soil. So like this, you see in two boreholes, you see a different depth, different specimens have been tested, and this kind of correlation has been developed. This is how it goes. So liquefaction resistance in the field is given, which is determined from the laboratory test in the form of cyclic resistance ratio CRR, and is the basis for calculating the cyclic stress ratio uh, in the CRR to find out the liquefaction potential. So here you see CRR. I don't go to further debate on that, but I would like to tell you that there are two kinds of liquefaction tests which are run in the laboratory. One is CRR-SS, simple shear, and the other is CRR-TX, triaxial. Both have some difference, and there is a correlation C sub R, which can be determined from this equation as a correction factor. But here I tell you that actually whatever test we carry out, whether SS or TX, we have to multiply with a certain coefficient to find out the actual CRR for the field. I mean, they give the higher value and it has to be reduced. That is the message. What I want to tell you, that the laboratory cyclic stress ratio of resistance gives you slightly higher value, and it's 80 to 90% has to be taken based on the type of the test for use in the actual liquefaction potential evaluation. So here you see, we calculated, as I showed you the formula in the beginning also, the cyclic stress ratio C sub R generated in the field because of earthquake, right? And we calculated the cyclic stress ratio CRR, which is because of the soil resistance. The ratio of the two, CRR or C over CSR, because of earthquake, like resistance over load, strength over load, same thing. It gives you some numeric value of factor of safety. So even one for less important work and for important work, a value like 1.1 of factor of safety is acceptable. This is how we carry out our routine analysis. I show you a round of these. Well, these are the factors on which depend. I don't want to spend too much time here. You can see various tests in a well. My answer to one question which was there, in situ test, SPT, you can see there's abundant database available, but control over the quality and repeatability is poor to good. And compared to the CPT, yes, that control is very good. Yes, we understand this thing. And soil sample is retrieved in SPT test, but there is no soil sample retrieved in the CPT. It's a limitation in CPT. One was that we cannot carry out to a deeper level, and the second is that we cannot see the soil even in which the test is being carried out. We cannot see that soil. So one has to make additional borehole adjacent to a CPT hole to see the soil type, to have a look at the soil type which is being tested by CPT. So it looks funny also to me. So similarly, look at the range, the shear wave velocity measurement, V sub S. There's limited database. And for the borehole pressure meter test, BPT, very less data. So resistivity will also fall in the same category. So use N values, you see, and N values have to be subjected to energy and overburden correction factors. I will not explain over here. But here you see, this is a standard graph, which because of the efforts of Professor Seed and Idris of Egypt, Professor Seed of USA and Professor Idris of Egypt. He was an Egyptian engineer who started living in USA and working under Dr. Seed, and then both worked together. They developed this kind of relationship. You can see the three curves shown here. On the top of the three curves is written percent fines, less than 5% or zero. SPT clean sand base curve or less than 5%. Then there is the intermediate 15% fine and 35% fine. On the horizontal axis is N160, the corrected blows for energy and overburden. You can see for any value of corrected blows, like you pick the value 10, as the fines increase, the cyclic stress ratio of soil resistance increases, right? You got it? For higher fine content, the liquefaction resistance will be higher. For clean sand, it will be lower. So you can also see inset a mathematical expression, which is a mathematical approximation on the basis of regression of these curves given in the form of a formula. But this straight away gives you the cyclic stress ratio of resistance. So they are the mathematical equations to calculate the same value. But I would like to tell you that this resistance factor has to be adjusted by a magnitude correction factor, the magnitude of earthquake. Why? Because our standard chart, this is the standard chart which is given in the literature to find the liquefaction resistance ratio. You can see in the note in the figure 2, this is for clean sand base curve and other curve for magnitude of 7.5. So basic, the data and the research is for magnitude 7.5, but say my earthquake is for magnitude 6. So I'll be using this graph to calculate the MSF factor, the magnitude scaling factor. Like I have an earthquake of 6 magnitude. So look at the horizontal axis, read against MW of 6. What is the average value? 2. So magnitude scaling factor is 2. So we will have to double the CRR value for this case to be multiplied, CRR to be multiplied with 2, or the ratio CRR or CSR to be multiplied with 2. So you see tremendous effect of the magnitude scaling factor on the liquefaction potential analytic results. This is very important correction factor. And you can see on the horizontal axis for the MW value of 7.5, the magnitude scaling factor is 1. Well, this is a baseline, you see. That is the baseline, that it is 1 for 7.5. For 8, it will be less than 1. And for all values more than 7.5 magnitude, the magnitude scaling factor will be fairly high. I think you got it. Some other factors which become multiplier for this equation of factor of safety. One is called K sigma and the other is called K alpha. K sigma is called the confining effect. If there's a confinement on the ground, some structure or some embankment is there, some hillock is there, and we want to calculate the effect of that on liquefaction, we'll have to adjust the equation by K sigma, apply a factor. And if there is a sloping ground, then its factor is K alpha, a sloping ground is said to establish pre-existing shearing stresses, inherent shearing stresses in the ground because of the sloping ground effect. So its factors are there which multiply in the equation below. Okay, so because the time is finishing, I just want to end up, K sigma can be read from these curves given by uh, 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 Thomas and Yode, these curves for different density materials, K sigma, right? So we are in a position to calculate the safety factors against liquefaction or to compare the two cyclic stress ratios. It is evident now that the cyclic stress ratio of resistance is CRR and the cyclic stress ratio because of the earthquake loading is CSR, right? So here the zone in which the CRR is less than CSR is the liquefiable zone very clearly. So that is the zone in which the safety factor is less than 1. I think understandable. So in this ground, you see the depth zone where the safety factor is less than 1, where the soil resistance is lower than the applied load because of the earthquake. So this is how we quantify, and this is the zone which needs improvement. And if we have to change the foundation type, we have to change in such a way that we can even bypass this zone. Yes, we can do it, or we can improve it. You see, there are several ways. So there is another, you see, way to calculate the liquefaction evaluation based on CPT data. Time is less. I want to show you something more important. I am skipping details. I think it needed 3 hours lecture. A shear wave velocity measurements, leave it. And this is generally a table you see sometimes developed to calculate the CRR value based on various coefficients at different depths and to calculate CSR value and then take a ratio of CRR over CSR, of course, after having multiplied with all the adjustments and coefficients to get the factor of safety. I will not be able to elaborate this also to you. And I will like to tell you that the cyclic strains have been used. The strains resulting as application of the cyclic stresses are the shearing strains. We can compare them with some threshold value of strains to find out the liquefaction resistance. Okay, it is stuck up.
मुझे लगता है खत्म हो गया सुहेल किबिया को फोन करो जरा तुम्हारे पास आ रहा है नजर आ रहा है लेकिन कौन
I'm sorry, my speaker was muted. I'm sorry. So
Okay.
I'm telling you that the cyclic strain is another measure. When you apply stress, there is a strain. When there is a shear stress, there is a shear strain. And like we have modulus, elastic modulus defined as stress over strain. So shear modulus is shear stress over shear strain. So the same CSR equation manipulated shear stress of shear strain terms divided by G value gives you the cyclic shear strain value. It is to be compared with the threshold shear strain value of 0.01. If the if the calculated shear strength value is less than 0.01, no liquefaction. If it is more than 0.01, liquefaction. It is not in the terms of factors of safety, right? So this evaluation is a bit different. So now I cannot explain to you the mitigation measures, that time is short, but you can just these things in detail, that we can have ground improvement or, ground reinforcement or ground treatment. And there's so many ways. I'll just be able to show you the figures. If you put surcharge, you increase the liquefaction resistance. If you provide stone columns, you provide the place to the pore water to escape in the voids. Hence, you improve the liquefaction resistance because you reduce the pore water pressures. So there are ways to improve it by dynamic compaction, by deep vibro compaction, by ramming, and by surface ramming, and you see, by deep compaction called vibro compactions, vibro float, a floating vibrator going into the ground and compacting and densifying the soils around it. And there are, you see, stone columns called vibro replacement, and concrete columns also. You see concrete pumped under pressure and columns made. So it's very common, and blasting is also done sometimes in the ground to induce liquefaction, because I told you in the beginning that after liquefaction, the post-liquefaction scenario is such that the ground gets densified. The voids reduce in the ground. So ramming and different kinds of grouting situations also help, and there are so many grouting and, applicability to the ground and post-liquefaction deformation. Let's skip it. I just wanted to take you to the last slide, perhaps. Not in yeah, this one. I just wanted to narrate 4-5 very, very briefly cases of the projects in the liquefaction. Potential was eliminated in Pakistan, under my experience. One is the Cheshma hydropower project, where Cheshma powerhouse was to be constructed 24 meters below the Indus bed level. The sands were in loose to medium dense condition, so it was opted to go for deep vibro compaction, and it was sufficiently securely done. So the project is there, and the powerhouse has been constructed on the deep vibro compacted sands 24 meters below the Indus bed level. At Guddu Thermal Power Station, vibro replacement was done in the loose to medium dense sand. That is construction of stone column with a vibratory process to improve the liquefaction resistance. At Kotadu Gas Turbine Power Station, I was there for units 4 to 8 and 1 to 4 and 5 to 8. And I remember that the upper zone up to 4-5 meters was liquefiable, but it was variable at the site. At places, it was liquefiable up to 2 meters. The groundwater was touching the surface, and at other places, it was like 3 meters, 4 meters. So, based on the studies of SPT, the whole area was zonified into zones of different, denseness requiring different depth of replacement. So, soil was simply excavated. The same soil was densely compacted and placed back in layers to mitigate the liquefaction risk. Uh, Another example in which many air bases of Pakistan, which is classified information, I will not be able to reveal much, but we had to design, me and my team, I had to design stone columns there, stones of uniform size, so that they have maximum void spaces in between. I didn't use stones of uniform gradation, so stones of well-graded gradation. I use stone of same 3 inches nominal size so that they have maximum voids. The soils were medium dense to dense. And the idea was, if there's a bomb and if there's a blast, and if it enters the ground up to a certain depth, then it should not, damage the underground works by liquefaction. The excess pore water pressure should be able to escape into the large diameter 1 meter diameter stone columns made of uniform stones with large voids. At Cheshma Nuclear Power Plant, at many of its works, simply confining pressures were increased by adding surcharge, several meters of surcharge, and then the power plants were made on the raised ground by making platforms. This would increase the normal pressures and would reduce the shearing stresses or the cyclic stress ratio generated by earthquake. So that is another way how we improve the safety factor against liquefaction by constructing in weak grounds, liquefiable grounds, on the surcharge, on the platforms. So thank you very much with this slide. But I'm still here if you want to put some questions. If there are some questions, I'm here.
Suhail, can you hear me?
Yeah, I can hear you very clearly.
Yeah, there are two questions
Yeah,
from,
please.
one is from Mr. Furkan. It is
Yeah.
in traditional tunneling where delay blasting is used for excavation. Can delays in blasting initiate liquefaction phenomena while tunneling through alternative hard and soft grounds? Alternative hard and soft ground conditions under water table.
You see, first of all, term of liquefaction should be used generally for granular soil and sands in general, right? And less often for clays unless they are sensitive, and should not be used for rocks, whether soft rock or hard rock. Is your question regarding soft and hard rock, tunneling in soft and hard rock, Mr. Furkan?
Furkan sir, you can
Mr.
answer.
Furkan, are you hearing?
Yes, sir, I'm hearing. Can you hear me?
Please talk to me.
Yes, I'm talking about the
Yeah, yes, Furkan, I can hear.
alternate beds of soft ground and hard ground, because I have experience of such
Well,
ground. Yes, where we have hard
what do you mean by
sandstone
hard and soft
and we
rock?
have,
Are you talking of presence of hard rock and soft rock?
yes.
Liquefaction definition doesn't apply simply to rocks.
Okay.
So no question of liquefaction. Next question.
Next question, just hold on. I will just today Zoom is bit unstable. I don't know why the screen keeps on changing. Let me check. Yeah, the second question is from Mr. Shahzad Shafiq.
Okay.
He's asking, what is the recommended earthquake magnitude to estimate soil liquefaction? For example, if a site-specific study is available that shows the site will receive a maximum earthquake magnitude of 5.4, I'm 5.4. I think it's Richter scale. He has, though he has not written. So we will estimate soil liquefaction at an earthquake magnitude of 5.4 or 7.5.
The standard charts available will always give you calculation of liquefaction induced, the cyclic stress ratio to be resisted by earthquake by soil strength for 7.5. You will multiply that with the magnitude scaling factor always, you see, to reduce it, to obtain it to the value for your actual earthquake magnitude. One. It depends on the actual strength and attribute of the ground, whether it is a strong ground, high SPT blows, I mean, or low SPT blows or intermediate SPT blows, which, which will get liquefied with this magnitude of earthquake. It is a low magnitude earthquake in general, you see, but if this same magnitude earthquake, if it happens close to surface, it will be able to generate reasonably high peak ground acceleration. So you see, it is an interplay. It's your answer. The question, your question doesn't have any answer. It is open. One has to calculate one has to find out that what is the peak ground acceleration. Magnitude alone is not enough, because the cyclic stress ratio generated by earthquake will depend that how much is the acceleration, which has a relationship to the depth of the epicenter of the earthquake, number one. Number two, the cyclic resistance ratio of the strength of the ground is a function of the strength of the ground, its state of cementation, etc. So you will determine both and then find out the ratio of the two cyclic stress ratios to find out the safety factor and to get the conclusion. It is a bit rigorous. G. Next, Right, Saab, any other question?
Last question. It is not a question, it is just a request. Sir, can you please share the notes? That will be very helpful for us. Well, I really don't know what do you mean by notes. If you mean about this copy of this lecture, all our lectures are loaded on our YouTube channel in a sequence 1 to 30. This is the 35th lecture. So you can find the whole lecture there available for free viewing. We don't charge any fee there for the YouTube channel. All the lectures are there, and this will also be posted there, I think today or tomorrow. So now if there is anything specific notes you are asking, you can come on the mic and ask about the notes.
My understanding of this participant from notes, I think, comes out or stems out from the feeling, because in university, I think nowadays a poor habit by some teachers, rather by most of the teachers, they just give notes and students are not aware of the textbooks or the research papers. They seldom happen to study the research papers or the textbook. So the rely of notes, I think they have the idea of notes perhaps of this kind. But Tahir, you have already amply replied that so far as the deliberation of my today's lecture, including slide and my voice is concerned, they will be on YouTube. And if nevertheless, if somebody wants to have some personal consultation for guidance, I'm available. I always am happy to mentor. If you really require something and you can ask me something, no issue.
Well, I can remind everybody that engineer Suhail Gibria is not, though he's a guest speaker today, but he's very much part and parcel of Pakistan Society of Civil Engineers. He's among the founder members of this society, and he's available 7 days a week, 24 hours to the society. So anybody wants to speak to him or send him a mail or a question, you can either directly send him a mail or you can send it to Mrs. Sadia, and that question can reach him in no time. So he's always available here. So any more questions? So please raise your hand so that I can see if anybody has to ask any question or I don't see any question typed in the chat box. So I think, Suhail, if there is no further any questions, or if you have any closing remark regarding liquefaction, you can do it. Otherwise, I will make further announcements and then we can close this session.
I will just like to ask the participants that since a lot of effort was made to prepare this lecture for the participants and to deliver it. Did they find it interesting? Did you guys find this interesting or boring? You know, it is just 2 hours, you see, in which we have to sum up. I did my best, you see. Of course, I know there's a lot more detail. There are books and papers and papers and books written on this topic. So I know full justice cannot be done in a matter of 2 hours. But did you get something? I'll be happy if most of you have got something new or come at least some prompts to further study and to further refine their concept about liquefaction. Taisab, can you ask them to raise their hands so that you can see and give me just a feeler? That will be my last comment.
Yeah, if I have already asked them that if anybody has to make any comment or observation and have any question, they can raise their hand. And otherwise, the feedback of the lecture from PSCE, a survey form will be sent to all the participants, and they can fill it and send their comments about this lecture.
Okay.
That we will get. So now I don't see any hands raised. So
Okay.
we end the. Thank you very much, Suhail. That was really a good lecture, and I mean, though it's also my field, I really enjoyed the lecture, and comprehensively you explained in such a short time. It was a summarized lecture on liquefaction, though it's a very wide field. More things can come, can be detailed in it, but due to the lack of, we have a certain limitation on the time. So you did it very well to cover liquefaction, the topic of liquefaction, and well done. So we end this section now. Maybe there is one, no, it's okay. Okay, so we will end this session here. Next lecture will be on 13th November 2021. It will be Professor Dr. Ali Rizwan, and the topic would be basic consideration and application of SCC in Pakistan. And same time it will be 2 p.m. 13th November 2021. So you can those who are interested, they can register themselves according to the procedure which you people know. And certificate, there is one announcement which I would like to make, that due to some unavoidable circumstances, PSC had to vacate their office in Gulberg, Lahore. The circumstances were quite unavoidable. So now, till we find a permanent place of our own, the office of Mr. Rizwan Mirza will be used till that time. It's located at 83M Model Town, Pakistan, Lahore. So 83M Model Town, Lahore. This is the place from where you can collect your certificates of today's lecture. After 13th October, after Wednesday, you can collect your certificates from there. This office will be available from Monday to Friday, and 10 a.m. to 4 a.m. This office, 4 p.m. This office will be open for you people to collect your certificates after 13th October, which is Wednesday. I again repeat, the new office location is at 83M Model Town Extension, Lahore. And those of you who would like to those who would like to make a phone call before coming to this office, then the mobile number is 0345 424 3404. 0345 424 3404. In case you have any difficulty in reaching this office, you can contact Mrs. Sadia Naveed on email, and she will assist you there. So these were the announcements, and Suhail, your shield and certificate, inshallah, will be dispatched by courier to your address, or somebody will deliver it by hand at your hand. Home, at your home. So that is where now I'm just checking if anybody had asked any question. Okay, Ji, I will just type the address. Somebody is asking me that I should type the address in the chat box. Just give me a minute, I will do it. Ji. So this is the address G83M Model Town Extension, Lahore. And phone number I will also type so that if there is any assistance required, you can call on this number. Suhail, I don't know whether you have seen in the chat box or not. Mr. Furqan has text the message. Thank you very much, Sir Suhail Gibria. I always enjoy and wait for your lecture.
Yeah,
So-
I've just read it. Yeah, I've just read it, and I've thanked him to Mr. Furqan. Thanks a lot. Keep waiting, and till I come next time, inshallah.
So I was just saying that if okay, I think now we don't have any further questions. So we close this session. Thank you very much for attending. Suhail, again, thank you for such a wonderful lecture.
Welcome.
Acha ji. Okay, ji. Thank you
Thanks.
very much. Allah bless you all.